Good morning, ladies and gentlemen. This is Ben Keyser with Applied Flow Technology, and I hope that you are all having a very fine week so far. Thank you for joining me in the webinar today on September 8th, 2019. And today we're going to be talking about how to model settling slurries in piping systems. And before I start to jump into things here, I want to show you where you can find more information on our website about each of our products. I'm sure that you all know where this information is, but if you go to AFT.com under the products menu, you can go to each of our products, Fathom, Aero, or Impulse, to learn more details about each of them individually. And then once you click on one of the products, if you scroll down a little bit further, you can find the section where we have specified our add-on modules for each product. And so the module that I'm going to be focusing on today is the settling slurry module for AFT Fathom and also for AFT Impulse. And they can help you avoid various problems when you're dealing with slurry applications. For those of you who are listening in live today, I have included a PDF of the slides of my webinar, and that way you can have those to go back and refer to later on at your leisure. And also the webinar is being recorded. That way you can send it around to your colleagues afterwards, or you can listen in again if you want. If you're listening in to the recorded version of the webinar, please email me at benkeiser@aft.com, benkeiser@aft.com, and I will be happy to send you a copy of the presentation. All right, let's go ahead and get into it. So I want to start off with a terrible accident that happened. It was the world's largest slurry pipeline in Brazil, and it was a iron ore pipeline which burst. And it contaminated the environment and caused a lot of bad things like health problems for people. The whole operation got shut down, and so it was a major loss of money for the company. Licenses can potentially be revoked to operate, and then you're going to have to deal with new expenses for tighter inspections. And so this is just a good case of a example of an accident that happened where it's really important to know what's going on in your slurry systems, because just like any pipeline, they can cause a lot of issues. But one of the things that is making things more problematic for slurry pipelines that you don't have to deal with non-slurry pipelines is plugging up the pipe due to solids settling out of the fluid if your velocities are too low. And so that can bring on a whole other set of problems that you may not always have to deal with in working with slurry applications. So why did that pipeline burst? Well, one source stated that there is a drop in pressure in the pipeline somewhere. And, there are a lot of different reasons. And when I was going through this, it was difficult to find consistent reasons across multiple sources. So let's talk about what could potentially cause a slurry pipeline to burst. Well, obviously, like I just mentioned, if the pipeline gets plugged up, when that pipeline gets plugged up and it just starts building pressure more and more and more, you're deadheading against that plug from your pumps, and that's going to be one thing that will cause your pipeline to burst. Other issues are where if you have not properly derated your pump performance for pumping a slurry. Keep in mind that obviously your test fluids for the pumps and their pump curves that you get from the manufacturer, those are typically tested with water. And so they're not going to perform the same when you are trying to pump a slurry through it. And the effect of solids on the pump is going to be significant, and it will decrease the amount of added pressure and flow than what you would actually be expecting. So if you're expecting a certain flow and pressure based upon the clear fluid, you're not going to get the same when you're actually pumping the slurry. So it's important to make sure that you properly derate your pumps. That way you have a powerful enough pump that can do the job for you. Other issues are where the pipes are not sized properly. If you have too large of pipes, you can get more flow, but the lower velocities is what causes the solids to settle out of the fluid, and that's what can plug up the pipe. However, small diameter pipes can be just as problematic, where over time, the solids will continue to erode the pipeline wall thickness, and then that can cause issues as well with eroding the wall thickness. So you have to find the right balance between large diameter and small diameter pipes. And that's why it's not just a guessing game. You can't just throw things in there and expect it to work. Doing a proper analysis can help you get the job done properly. Lastly, elevation changes have significant effects. And if you are not assuming your elevations are changing, then that can cause issues with your system as well. All right, so what's the solution? How can you get around this? Should we ban or eliminate pipelines, or add more regulations to prevent new pipelines, or shut down existing pipelines? None of these are really good solutions. It's like if only a doctor could bring you flowers to help you feel better. It just doesn't work. So what's the proper thing to do is to build and design and analyze your system properly before you put it into operation. And so if you properly design your system and analyze it from different operating cases, there's a lot of terrible incidents that you could prevent from happening down the road. So you design the system based upon the project requirements, and then it's really important to do an analysis to help validate the safety of your design. So if you have a certain design and you want to build a model of it, the model will tell you if you're actually going to be able to get the expected flow rates and pressures and velocities, and it'll tell you if the design is actually going to work. So that's the first step. Another thing that you can do with flow analysis is to check and see how future expansions or retrofits on the system will affect things. And they can always have unintended consequences. So if you're putting in an expansion to your pipeline, you want to make sure that it works. Another case to analyze is what happens under abnormal operating conditions. So maybe something is causing your flows to drop by 20%. Well, that would be a case that you'd want to study to determine if you're going to start having any solids settling or not. And then it's important to simulate what can happen in accident or failure scenarios, such as pump trips. Well, if you're pumping a slurry and your pump trips, then you're going to have a major drop in pressure and potentially a lot of settling out of the fluid. And that's a slurry hammer problem. And that's what you would be able to use AFT Impulse for with the SSL module. So how can you perform a quality analysis for slurries? Is by using the add-on module SSL for AFT Fathom and AFT Impulse. Give me 1 second here. Excuse me. All right, so here's a basic description of what the settling slurry add-on module can do for you. It allows you to address the effect of solids being transported in liquids. And what we're using for the calculation methods comes from the slurry transport using centrifugal pumps book. And this is an excellent slurry course that is offered in, I believe, Georgia. And so if you're dealing with slurry applications, I would highly recommend that you would attend a slurry course, either by GIW, or you can also attend the slurry course by the Saskatchewan Research Council in Saskatoon, Saskatchewan, up in Canada. And both are excellent courses that will educate you really well on how slurries perform. The labs that you would be doing are excellent, and it'll really help make a lot of sense out of things. And so we've incorporated the GIW method calculations for the SSL module for Fathom and Impulse. Some various features that are really helpful is you have the ability to define your own type of solids in the fluid that you're trying to pump. You can actually account for the pump derating factors when you're trying to pump slurries. And we use the various standards, and I'll show you that here in a little bit for calculating those pump derating factors. You can generate slurry specific output parameters like your IM and JM head gradients, slurry specific graphs like a slurry system curve, and basically everything that you need to evaluate your slurry system effectively is what can be done with the SSL modules. So before we get into jumping into the software here, let's talk a little bit about settling slurries in general. There are different ways that you can categorize them, and some slurries would not actually even be slurries in the sense that they can settle out of the fluid at all. That would be an example of a homogeneous slurry. This would be a non-settling slurry, such as the case where you have very, very fine particles. So if you have very, very small, fine particles, and you have a fairly homogeneous mixture that you're pumping, then those particles are not going to have a tendency to settle out of your fluid. And in fact, they're typically going to be more of a non-Newtonian performance, which AFT Fathom and AFT Impulse can do. You would use potentially a power law non-Newtonian model, or a Bingham plastic, or maybe a paper stock. Any of those options would be considered a non-settling homogeneous slurry that you would not actually need the SSL module for. So if that's your case, then you would be able to potentially model it simply with standard Fathom and Impulse. The next category is a pseudo-homogeneous slurry. So this is where you have a settling slurry in a fully developed turbulent flow. And so you have a little bit bigger of particles, but everything is moving turbulently. And it is possible that the solids in that case could settle out of your fluid if the velocities are too low. The next category is a heterogeneous slurry. That's where your slurry is flowing with particles in a non-uniform distribution. I'm going to show you pictures of all of these cases here in just a minute. The next case is a sliding bed. So that's where some of the particles have started to settle out into the bottom of the pipe, but there's still enough velocity of the fluid to keep the pipe, or to keep the solids moving down the pipe. So the velocity picks up some solids, and then it carries them a certain ways, and then it drops them. And so that sliding bed is where your solids just keep moving down the pipe a little bit at a time. And then finally, there's a stationary bed. That's where the velocity is way too low, and your solids just start collecting at the bottom. They're not flowing, and you're going to end up with a plugged up pipe. So the SSL module can help you with the three middle categories: the pseudo-homogeneous, heterogeneous, and sliding bed. And now we're going to see what those look like here on a slurry system curve. So if we were to look at a slurry system curve with our pressure gradient as a function of velocity or flow rate, we have the same categories I already talked about, except for the first one. The homogeneous category is way out up here. So the homogeneous category where you're more of a non-Newtonian fluid and you have very fine particles, there's virtually no chance that that's going to settle out of the fluid. So that's why it's not even included on this graph, because it's way out of the category of, what would be a settling slurry. Here's the pseudo-homogeneous mixture. So this is where you have particles that are big enough to settle out of your fluid when the velocities are too low. But if they're moving along in a turbulent flow regime, and you can see how it's a fairly homogeneous, uniform mixture, this is a good place to operate at right here. And this will effectively pump your slurries through the pipelines. this is where you want to operate, as far up on the curve as you can. But if not, at a little bit lower flows, you would have a heterogeneous category, and that's where you're still pumping your solids down the pipeline, but it's in a non-uniform distribution. So everything is still moving smoothly down the pipe, but you're not going to have a straightforward uniform mixture there. So it's okay to still operate there, but you'd want to try and operate further up at higher rates of velocity. And then finally, we have the sliding bed category. The sliding bed category is where your velocities are not high enough to maintain continuous flow, and your solids will be picked up at one port of the pipeline and then dropped at another point, and then they'll just keep, edging along the pipeline over time. So that's the sliding bed category. And then the case where you definitely want to avoid is this point right here. So the goal is to operate to the right of this curve, because if you start to operate to the left at lower flows where you have higher pressure gradients and this curve begins to increase, that's your stationary bed category. That's where you're plugging up your pipe and it's going to start causing major operational problems. This is a very helpful graph that you can actually generate in AFT Fathom with the settling slurry module. And so if you are generating a graph for the slurry system curve in this fashion, you would want to make sure that the velocity or flow rate that you're operating at is to the right of this minimum point right here. And so that will give you an indication of what type of slurry that you're pumping in those cases. Excuse me. All right. Okay, let's talk about the settling velocity itself. The settling velocity is dictated by this curve here. So as I follow along that curve with my beautiful artwork, this is a pressure gradient versus velocity. This is the limiting velocity in which you will start to have solids settling out of your fluid. So this curve right here is called VS. That's for your settling velocity. So the thing I want to point out is the settling velocity here is different than the settling velocity here. Now, VSM, this is the maximum settling velocity. So as you can see, when you follow this curve around here, this is the point at which you have the maximum velocity where you would operate past, and that would be the absolute limiting case where you would start to settle out of the fluid. And so any velocity at this particular point right here, it is possible that you could start to have settling. Now, let's go back to the concept of just the VS parameter, your settling velocity itself. Your settling velocity is not independent of concentration. So as you can see, for each of these points of the settling velocity, it is different depending on the concentration of solids that are present in your slurry. So as you get to have higher and higher concentrations down here, the velocity at which they could start settling out would be less. Now here's the thing. The advantage to considering the VSM parameter, your maximum settling velocity, is because it is independent of concentration. So when you're comparing your operating velocity, this is just your average velocity of the slurry in the pipeline. If you are operating a velocity higher than what the VSM parameter is, the maximum settling velocity, then that's going to give you the best assurance that you're not going to have settling in your pipeline, because it doesn't matter what the concentration is. So it is okay to pay attention to what your settling velocity value is, but something that is more of value is the maximum settling velocity itself, and you want to try and operate at velocities higher than that. Okay, these are just some basic slurry applications, lots of mining applications, moving waste materials, dredging applications. So if you're trying to dredge out an area for ships, then that would be an application where you would need to deal with settling slurries. So there's probably a lot more that you know about that's not included in this list. It's just a very small sample. Okay, so these are just some different things that the settlement slurry module can do, and I'm just going to breeze past all these, and you can read through those bullet points on your own because you have the slides, and I want to try and start getting into the software itself here. One thing I do want to mention is AFT Fathom, you do have the ability to model heat transfer with your settling slurry. So if you're operating in a very cold environment and cold temperatures are a problem, then you can model heat transfer to maybe figure out how much heat tracing you might need in order to keep the fluid warm so that it flows better. And so that's an advantage with using Fathom, is you can still do heat transfer calculations with your settling slurries. Okay, so this is the first example that I'm going to show you here today. It's a very simple pumping system where we are pumping sand from one sand pit to another. So the supply sand pit is here, and we're discharging it to this receiving tank, and there's some things that we want to calculate. So the things that we want to be able to determine is we're going to size a slurry pump to transfer 25% sand slurry by volume. Our goal is to pump 1,400 tons per hour of the solids itself. When I get into showing you this example here, there's different ways that you can define your flow. You can either define your flow in terms of just the clear fluid itself or the slurry flow rate. The slurry flow rate includes both the liquid and the solids moving together. However, this is a case where I want to specify the flow rate of the particles themselves. So if you're trying to move as many particles or solids as you can, then that might be where you would have a requirement on the solids themselves rather than just the slurry itself. There are 3 slurry calculation methods available. I'm going to show you what those are. We're going to use the detailed method, and then the standard that's used for derating the pump is a ANSI HI standard for determining the pump derating factors, and we're going to use 12-inch diameter pipe. So let me go ahead and open up that model really quick here. That's the next example that I'll show you. All right. Let's see. Where's my example? Oops, I'm in the wrong software. I need to be in Fathom. Sorry about that. They all look alike. Actually, that's a really solid advantage is when you're learning our software, if you know one of them, you know how to use the other. So if you learn Fathom, you have a really good handle on how to use AFT Impulse or AFT Aero. In addition to that, if you're starting off with a Fathom model where you're doing a steady state calculation, and then later you need to do a water hammer analysis, you can just import your Fathom model right into Impulse. That way you don't have to rebuild it from scratch. Okay, so here is my model, but before we get started, how do you turn on the settling slurry module? Well, there's a little button right here that is just to the left of the status light. If you click on that button, this is one way that you can turn on the settling slurry module. And if you have access to a license for SSL, then that module will be accessible for you. And then it'll check the box, meaning that it's turned on. Other ways that you can turn on the settling slurry module is from the tools menu and then activate modules. And you can also turn it on from the very beginning in the startup window. So that's how you turn on the module. The next thing is when you turn on your add-on, when you turn on the settling slurry module, if you go to the analysis menu for slurry modeling, you can either model the settling slurry itself or you can disable it. Why would you want to disable it? Well, let's say that you already entered all of the slurry information for your solids particles, the standard that you're using for the pump derating factors, different things like that. But you want to do maybe a scenario where you ignore that and you're simply just wanting to do a regular calculation with Fathom, and you don't want to have to delete all that information. That's where you would maybe disable the slurry calculations. Now, if I go to my system properties window, this is where you define the type of slurry that you're dealing with. And as I mentioned, there are 3 calculation methods: minimal, simplified, and detailed. The blue highlighting represents required input. So if I click on minimal, the only things that I need to specify are the densities of the solids, the temperature of the fluid, and then the concentration, as well as the sliding friction coefficient. So minimal is the least amount of input that you have to specify. This will give you a very quick calculation. Maybe you don't have a whole bunch of other information and this is all you got. This is a good way to start things off if you don't have enough details on your slurry yet. Or maybe you just want to do a feasibility study or sensitivity analysis. Simplified is the next most detailed, and or where you would need the next most amount of input. You would specify your stratisfaction ratio exponent and then the D50 particle diameter distribution. Now, I'm not going to define what those parameters mean. This is not intended to be a SSL training session. The slurry book from the GIW course that I mentioned earlier, that contains all the terminology on slurries. And then we also teach a settling slurry training seminar with AFT Fathom. So if you deal with settling slurries, perhaps we could come out and train you on Fathom as well as a slurry module, and then you'll learn all the terms as well. Just know that there's a little bit extra information you have to specify when you use the simplified method. Finally, the detailed method is where you have to specify the most amount of information, which is still not very much. Now let me cancel that and go back in. So here, when you use the detailed option, not only do you have to specify your M factor or have it be calculated, you'd also be able to specify your terminal velocity, your D85 particle distribution, etc. So those are all different ways that you can do your slurry calculations. And then there's basic water slurry input and advanced slurry input. What is that? Well, if you're using the basic water slurry input, this is just a very simplified option where your carrier fluid of the slurry is going to be water. And you're specifying the temperature of water. So it's nice and easy. However, let's say that you have a different carrier fluid other than water. That's where you can do advanced slurry input. So if you do advanced slurry input, this is where you can then access any of these different fluids for your carrier fluid that's bringing about the particles. So you can access any of those if you're not pumping a water as your clear fluid. This is also where you can do heat transfer calculations with slurries as well, is by using the advanced slurry input option. Now today we're just going to keep it simple and use basic and system data. That's the same as it was before, and we're ready to go. So now that I have specified which calculation method I'm going to use, you just go through and you define your input like normal. And so I've got a 5-foot liquid elevation with a 10 psig surface pressure on top. So maybe this is a pressurized tank. And then we have 12-inch diameter pipes, as you can see, 20 feet long. This pipe here is 500 feet long. And then this pipe here is 50 feet long. Now let's take a look at the pump. So for the pump, I'm trying to size my pump in order to get a slurry pump that will meet this application. So the option that I've chosen is to use centrifugal, but I'm using the sizing option right here. That's where all I need to do is specify a fixed flow rate. Fathom will then calculate the pump head or increase in pressure that's needed to overcome system resistance and elevation change. So my desired flow rate is 1400 tons per hour. You can change the units with the drop-down menus. And as I mentioned, this is where you can specify if that's a flow rate of the slurry, the solids themselves, or the clear liquid. So in this case, I'm using solids. That means that the actual slurry flow rate of the liquid and the solids together is going to be higher than 1400 tons per hour. Lastly, I want to make sure that I derate my pump properly, and there are different methods that are available here. The ANSI HI standard is a good one, or you can use the Warman method or do a user-defined derating. And so here you would specify the percentage of fines in your fluid and then your impeller size, and then that will calculate the derating factors for you via the HI ANSI standards. So now that everything's all set up, let's go and run the model and get some results. Okay, so the calculations are all completed, and we'll go to the output window. Here's something that is a little bit new when you're dealing with a settling slurry. There's a new slurry tab in the pipe section. So this is where you can find slurry specific output parameters like your IM and JM head gradients, your settling velocities, your settling velocity ratios, etc. How do you dictate which settling slurry parameters that you're dealing with? Well, that's the output control window. You can open up the output control with this spreadsheet looking tool with a pen on it. Either of those will work. So when you open this up, this is where you can specify the list of all the parameters that are available and pick which ones that you want to display in the output table. So the slurry specific parameters are all the way at the end, right here. So if you click on that slurry button, then you can access the slurry specific parameters. So CHW, this is your effective Hazen-Williams factor. You can add your concentrations, your mass medium particle diameter, your diameter for which 80% by mass of the solids are finer, your IM and JM head gradients. And so the key thing is, if you're not sure what any of these parameters are, just look at the description down below. So these are the parameters that I'm currently showing. Now let's go ahead and take a look at the flow rates. I am currently showing the mass flow rate here itself. And I'm going to change the units to tons per hour. So here's tons per hour. I'm then going to also show the mass flow rate of the liquid. I'm going to put that right after, and the mass flow rate of the solids. And I'll change these to tons per hour as well. Tons per hour and tons per hour. Okay, so my desired flow rate is to get solids flowing at 1400 tons per hour. So that is good. That is exactly what I was hoping for. But then here's the overall mass flow rate of the entire slurry. The liquid itself is 1,450 tons per hour. When you add those two together, your actual amount of total mass through the pipeline is 2,850 tons per hour. So that's how you can distinguish between if you're getting enough solids transport or not. Let's take a look at the slurry system curve. So I'm going to go to the graph results window. And when you're dealing with settling slurries, there's a new tab, slurry system curve. And what I want to be able to generate is a curve that looks something like this. So I'm going to do a pressure gradient and velocity. So I'll just keep it as it is, and I'm going to generate my curve. And so I'm actually going to do this in terms of mass flow rate instead of velocity, because I know my mass flow rate is tons per hour. And that's, oops, wrong tab. So 2,847 tons per hour. So here is where I'm operating at. And this is way past that dip at the minimum of the curve. So this is where I'm actually operating, and that's good because I'm avoiding a sliding bed. So this tells me that the 12-inch diameter pipeline is a good diameter to be able to get the flow rate that I want and not have any settling. But then I also want to check my pump derating factor. So if I go back to the output window, under pump summary, this is where you can add in your derating factors for corrections on efficiency, head, and flow. Let me remove these and then re-add them again. Okay, so as you can see, in order to get this flow rate through the system, the efficiency is actually going to drop by 23%. And the amount of pressure gain across your pump is going to decrease by 21%. So you want to make sure that when you're sizing your pump, this is your operating point for flow and head. You have to make sure that your pump can actually accommodate 21% extra head in order to appropriately pump at these operating conditions. So this is your derating factor, and that's what you need to account for in order to properly size your pump. All right, so this is just a very basic example, and it comes right out of our walkthrough tutorials. So if you're in AFT Fathom and you want to be able to figure out how to reproduce this example, and you have the slurry module yourself, you can. You can go to help and then show examples, pick your desired units, and that brings up our examples help file, which is our walkthrough tutorial. If you expand the Fathom module section, the settling slurry is where you can find the example. Pump sizing for sand transfer system. And this will walk you through, this will walk you through the very basic example of how to build the model from scratch. Now, if you do not have access to the SSL module, you can still open the help file and read through the example yourself. That way you can still learn about it, but you just wouldn't be able to build the model itself. In addition to that, you can open up the examples help file without having to be in the software itself. So if somebody else is using the license and you don't have access to it at that time, but it's installed on your computer, you can browse to where Fathom is installed, which is typically on the C drive, and go into the examples folder, and this is where you can find the same examples help file. So that's how you can open it up without having to be in the software itself. Now, another thing I want to point out is the verification folder. If you go to the verification folder, this is where we have cataloged all of our verification cases. And this is a verification help file where we've documented everything. What we have done is we have built models of several published examples from all of these different references, and resources. And as you can see, there are several cases where we are validating the slurry calculations in Fathom with the slurry calculations from the GIW book that I mentioned earlier. So if you want to ensure that Fathom is doing the calculations properly, you can refer to each of those cases and you'll see that Fathom is calculating the same results that the GIW book is. I call it the GIW book because that's the course that teaches those methods, but make sure you don't do a search for GIW book. Make sure you search for the actual title in my slide earlier. Okay, so I've gone through this example for basically all that really needs to be covered here. Let's move on to the next one. So here we have a bit more complicated of a system. It's a longer pipeline, but again, it's not that much different because we're still taking sand from a supply sand pit and we're pumping up to a receiving pit. However, there are some differences where we have changes in elevation, such as at this location right here, and we're going to see how that affects things for our calculations. So we want to determine our pump head requirements, verify pipe sizing, and we're going to examine the average velocity to maximum settling velocity ratio, the slurry system curve, and we'll look at the pump derating factors. So let me go ahead and open up that example here. Okay, so I'm going to look at the detailed. The initial pipe size is to use 12-inch pipes in diameter. And so as we take a look at the model data window, everything here is a 12-inch diameter pipe. We can see the pipe lengths that we're dealing with, reasonably long, and we can see that we have some elevation changes. So we're starting off at 0 feet. Our pump is at a 4-foot elevation above, and then we have our 4-foot elevation here, and then it increases to an elevation of 30 feet. So we have a 26-foot elevation change between these 2 points, and then at the receiving pit, it's also at 30 feet as well. So that's our pipeline where we have some elevation changes. If we open up the system properties window here, we can see the slurry calculation or characteristics that we're dealing with. And here's the D50 and D85 particle size distributions, as well as the shape factor that we're using. And this is a sand by volume of 20% concentration. It is possible to do your concentration in terms of either mass or grams per liter of mixture, but the common way of defining your slurry concentration is going to be by volume. That's your typical concentration there. And then for my pump here, I'm trying to, I want to supply 5,000 gallons per minute of the slurry itself. Now, one of the things that I needed to look at is the VM over VSM ratio. The initial size is 12 inches in diameter. I need to verify the pipe size. What does that mean? Well, am I going to have any settling in the pipes? Are any solids going to start falling out of suspension? That's what I need to look at. And a very helpful parameter is the VM over VSM ratio. So if you're comparing your operational velocity, which is the average velocity, to the maximum settling velocity, and if that ratio is greater than 1, that means that you're pumping at a higher velocity than the maximum settling velocity, and that's good because your operating velocity would be higher than the highest settling velocity, which is not dependent on concentration. So this is a very important parameter that we're going to examine when we do the results. Excuse me. All right, let's run the model here. Okay, so we ran the model. We don't have any warning messages. That's good. We have our dimensionless gradients for IM and JM. Our operating velocity is 14.3 feet per second in all of the pipes. Now, if we look at the maximum settling velocities, we can see how those values change. Why is it that the maximum settling velocity values change in every single pipe, even when the velocity is the same in each pipe? Well, the reason why is because of the elevation changes. The elevation changes themselves will actually have an impact on what your maximum settling velocity is. So keep that in mind when you're pumping over a pipeline. You have to ensure that your operating velocity is higher than your maximum settling velocity, which is going to change throughout your pipeline. Now, this is a very helpful parameter. It's the VM over VSM ratio. And as we can see, for the pipes which are at a elevation change and they're not horizontal, the VM over VSM is much closer to 1 than what I'm comfortable with, versus the horizontal pipes, which are at a factor of 1.3. So this is where you really need to make sure that you have a high enough velocity to effectively transport your slurries. You can also see what the pipe angle is. This is a output parameter. How do you get this parameter? Again, go to the output control window, which is either of these two buttons right here. And then when you open up the output control window, click on slurry, and then scroll down in the list of parameters for pipe angle. And this is where you can add your angle of the pipe for positive flow. And that way you can easily spot which pipes that are at an inclination. Those are going to have lower settling velocity or higher settling velocity values. So that's important to pay attention to. So let's try using a smaller diameter piping. So instead of using 12 inches of diameter, let's use 10. So all my pipes now are 10 inches in diameter, and let's see if we can increase that VM over VSM ratio. Well, we do. So when we use a when we use a smaller diameter pipe, we get a higher velocity, and that's going to be more effective at pumping the solids. And then you can see here the impact on the VM over VSM ratio. All of the VM over VSM ratios are well above 1.5. So that means your velocity is 1.5 times higher than the maximum settling velocity. That's good. That means that you're not going to be in danger at this operation of having any solids settling out of the pipe, plugging up your pipeline. So using a smaller diameter pipe is more effective at pumping your solids. But here's the thing though, is that you have to be aware of erosional velocities as well. As your velocity increases, you're going to have solid particles tearing away at the wall thickness of the pipeline itself. Now, how do we calculate the erosional velocity? Well, we don't. That's not a calculation that's built in. The reason why is because it's not just a steady state value. That erosional velocity, it's going to be something where it has to, be there for a long period of time. So it's more of a transient thing for how long your velocities have been operating at a very high rate, which is going to start to erode your pipes. So this is where you have to find a balancing act, and so you want to make sure your velocities are high, but not too high. All right, let's take a look at our pump derating factors now. So if I derate my pump performance, nothing has changed in the system. The only thing that I have done is I have turned on the slurry derating factor. So here, I actually have some fine particles in the slurry, and my impeller size is going to be 26 inches in diameter. And I still have my 10-inch pipe diameter system. So this information is all the same as it was before. But when you look at the pump summary here, we can see that we've got correction factors where for our flow and pump head, we need a pump that can actually generate about 5 feet or 5% higher head for 5,000 gallons per minute. That way, we'll ensure that we have a high enough flow and a high enough pressure when we size our pump. And then we can always take a look at the slurry system curve as well. And so our operating point is 20.34 feet per second, which is right around here. So we're doing really well with our slurry pumping. But let's take a look at the 12-inch diameter system and see what that looks like. So here's my 12-inch diameter system. The operating point is 14.3. So if I find 14.3, which is this, that's where we're operating. As you can see, that's where we're going to be starting to get really close to a stationary bed category, and that's definitely what we want to avoid. This is why we needed to decrease the diameter in order to increase that velocity, and that's how we can ensure that the 10-inch diameter pipe is going to give us a much better operation. Wrong curve. There you go. So now 20.34. This is the closest data point. If convert that to an annotation, and that's where you can highlight a data point right on the graph itself. So really useful for pointing things out. Okay, so that's enough for steady state slurry calculation methods. Let's talk about slurry calculations in terms of water hammer or slurry hammer with AFT Impulse. So what's different about AFT Impulse? Well, the main thing is that the wave speed has to be adjusted to account for the presence of solids. Now, this is not a webinar that is an introduction to AFT Impulse. So I'm going to assume that either you know a little bit about what AFT Impulse is doing for water hammer, or that you're going to go learn a little bit more after this. So one of the key parameters to defining how fast sudden pressure and velocity waves propagate throughout the system when you have a event like a valve closure or a pump trip or something like that is the wave speed. And so when you are using the settling slurry module with AFT Impulse, the wave speed equation has to be adjusted due to the presence of solids, and this is the adjusted wave speed equation here itself. So that's one of the main advantages with using the settling slurry module with AFT Impulse. So let's take a look at this example here where we have a slurry pipeline that is pumping to two separate deposits. Both valves are initially open, but one of them is more open than the other, and the operation that's causing things to change in the system is one of the valves is going to close a little bit and the other valve is going to open up a little bit. So it's going to shift flow, some of the flow from one tank to another. What we want to ensure as a design requirement is that the ratio of the mixture velocity to the settling velocity has to be greater than 1.2 for continual operation. That's simply your settling velocity ratios I've already showed you. So the question is, will the selected pipes allow acceptable velocity ratios? So we might need to change the pipe sizes in order to meet that requirement. So let's go ahead and take a look at this. Let me open up the model here. All right, perfect. So we have our settling slurry module turned on, what I'm going to do is I'm going to display the the nominal sizes of the pipes on the workspace itself. And so I'm just making a very quick modification here. I want to show the pipe number and the pipe size. So as you can see, many of the pipes are using 10 inches in diameter. I don't like how things are fairly cramped together, so I'm going to select everything and I'm going to scale up the workspace and spread things out by 200%. And then I'm going to make my text size larger. There we go. All right. So here's our system that we have in place. And if I look at the operation of the valves, here's valve number 1. The fully open CV value, or the CV value it's operating at, is 500. And I'm going to decrease the CV from 500 down to 300 over a period of a few seconds. So nothing is changing in the first second for this valve, but then it's going to take 5 seconds to go from 500 down to 300. So this valve is partially closing a little bit, which is going to restrict some of that slurry flow to deposit number 1. Then deposit number 2, this valve is starting off at 400 CV, and it's going to, from the very beginning of the simulation, increase from 400 to 500 in 5 seconds. So we're shifting flow from deposit 1 to deposit 2. And then for our pump here, we have a pump curve that's being used. We could derate the pump performance, but we're not in this particular case. And then here's all of our characteristics of the slurry. This is one of the slight differences in the impulse settling slurry module is that you have the bulk modulus of the slurry that you have to specify. That's not something that's needed in Fathom. So this is where that value is required for doing slurry calculations with AFT Impulse. All right, let's take a look. What are we doing here? Oh, got to section our pipes. And then I don't think that that's actually going to take 38 minutes. Let's see. No, definitely not a 38-minute runtime. That should definitely be avoided. Thankfully, my computer is going a lot faster. So we're going to monitor the impact of the slurry on this operation here. Now, one thing that I've done is I've defined a design alert. I went to the tools menu, and then under design alerts, I created a design alert for the velocity ratio. This means that the velocity ratio for all of these pipes has to be greater than 1.2. That's really useful because in my results, if I happen to have any design alert violations, I'll have very clear warning messages, and it'll highlight those violations in the output table as well. But using the output window is not the best way to analyze the results, so let's do some graphs. Let's take a look at the velocity ratio versus time. So here, what we can see, this is for pipe P4 and P14. That's P4, and this is P14, and we are looking at the inlet of each of those pipes. So the inlet, if we look at the elevation, we've got 4-foot elevation, 4-foot elevation, 30-foot elevation, 4-foot elevation, 20-foot elevation. So we're looking at the velocity ratio of the inlet of those pipes, and if I cross-plot my design alert, you can see here that as the flow has shifted from one tank to the other later on in the simulation, we are below our design requirement of 1.2 for the velocity ratio, and that's bad. So here, the sized pipes that we're using in this system are not going to work. Now, what we're going to do here is we're going to try using a larger diameter pipe on the suction side, the suction and discharge, before we split the flow. Because if we can allow more flow through the common header, then that can help overcome those velocity ratio violations. So let's see how this works out for us. While this is running, if anybody wants to try out the settling slurry add-on module and you do not already have access to it, please feel free to contact us or contact your channel partner if you're outside the United States, and we'll be happy to set up a evaluation license for you. That way you can try it out for yourself. All right, so if we look at our results here, we don't have any design alert violations. The minimum velocity ratio is above 1.2 for all of the pipes, so that's good. If I go back to my graph results window and I plot my velocity ratio versus time with my design alert, we're well above that. And we can also take a look at how the pressure changes as well. So this is the flow path to deposit 1. And I'm showing the maximum and minimum pressures. And if we did an animation here, we would be able to see how the pressure changes over time. It's a very slow change. And then now, as you can see here, we're starting to get some very slight changes in our pressure profile. So that's just another thing that you can look at when you're doing your slurry hammer analysis. You definitely don't want to have slurry hammer. That can cause some really major issues. All right, well, that basically covers it for today. Thank you all very much for listening in on today's webinar on how to analyze settling slurries and piping systems. If you have any questions, please feel free to contact us. Otherwise, take care and have a wonderful rest of your week.